Good day. This is the recorded lecture for Chapter 15. It's scheduled for Week 10, and Chapter 15 covers air, weather, and climate. This is a chapter that introduces some basics about weather and climate, but also really discusses the basis and background of the climate change issue. So if you are interested in this issue, you probably want to read this chapter rather thoroughly. This is a current Google Earth image that I downloaded of Greenland, taken in late 2012, according to the time stamp. Oh, actually, it's 2013. And I compared it to a satellite photo from a USGS publication from Greenland in 1992. Although the angles are different, you can kind of see how the ice extent in these two photos. So this is roughly a decade apart. You can go to Google Earth and explore Greenland and the Arctic ice sheet yourself. And you can also compare this image to the image shown in your book from 2008. The frozen cap of the Arctic Ocean, which is just north of Greenland, appears to have reached its annual summertime minimum extent and broken a new record low on September 16th, 2012. This is according to data from the National Snow and Ice Data Center, called NSIDC. Analysis of satellite data by NASA and the NASA-supported NSIDC shows that the sea ice extent shrunk to 1.32 million square miles. So this shows that Arctic sea ice is disappearing at an accelerating rate. So your book reports that in 2008, the summer extent shown was the lowest on record at the time, and we've even broken that record now. Figure 15.1 in your book shows that observed temperatures have increased in recent decades. So you can analyze this graphic a little bit here. The blue lines show uncertainty around global averages, which are shown in red. In the summer of 2010, Russians suffered the worst heat wave in 1,000 years of recorded Russian history. In Moscow, temperatures exceeded 100 degrees Fahrenheit for the first time in history, and the death rate doubled from heat stroke and lung ailments caused by smoke from burning forests and peat swamps. Let's update this to 2012. The number of natural disasters per year has been rising dramatically on all continents since 1980, but the trend is steepest for North America, especially in 2012, where countries have been battered by hurricanes, tornadoes, floods, searing heat, and drought. This is a report that was published by a Munich-based insurance company. The report finds that weather disasters in North America are among the worst and most volatile in the world, where we live. North America is the continent with the largest increases in disasters, says the report. The intensities of certain weather events in North America are among the highest in the world, and the risks associated with them are changing faster than anywhere else. Some specifics from this report: the second costliest year of the study period, 2011, was dominated by strong storms. Insured losses in the U.S. due to thunderstorms alone was the highest on record at an estimated $26 billion, more than double the previous thunderstorm record set in 2010, just a year earlier. Insured losses from disasters averaged $9 billion a year in the 1980s. By the 2000s, the average soared to 36 billion per year. Although some of this is disputed in terms of the fact that climate change may be actually influencing these increases, insurance companies have a stake in this game because they basically insure us and charge us rates based on their assessment of risks from various things, including natural disasters. But the evidence is mounting about this. This graph here shows that trends in climate from 1850 to 2000, and you can see the increases there. And part of the problem with climate change is it's one of those issues that needs a large body of evidence to support any conclusions, which we will look at later in this chapter. So chapter 15 first looks at how our climate works, causes of climate variability, and then we can take a look at the climate change issue and then maybe what to do about it. Among climate scientists who study the data, there's really no longer any debate about whether our carbon emissions are triggering climate change, or whether that change is likely to be extraordinarily costly in both human and economic terms. Remaining debates are only about details, how fast sea levels are likely to rise, or where drought will be the worst, or about fine-tuning of climate models. Among policymakers, it's another matter. Politicians are responsible for establishing new rules to reduce our carbon output, but many still have a hard time understanding the connection between climate change and the increasing incidence of forest fires, drought, water shortages, heat waves, and pest outbreaks. Energy industry money also plays liberally to sow doubt in the minds of policymakers and the public. Climate changes are gradual, proceeding over decades, so it's hard to get the public focused on remedies today. Many politicians have hoped for a silver bullet, a technology that will fix the problem all at once. Perhaps nuclear fusion or space-based solar energy, or giant mirrors that would reflect solar energy away from the Earth's surface. While these are intriguing ideas, none are workable now, and climate scientists are warning us that immediate action is critical to avoid tipping points, such as the loss of polar ice, ancient Arctic permafrost, and glaciers. So, some authors from Princeton University, Stephen Pikala and Robert Sokolow, have come up with this idea called wedge solutions or wedge analysis. Wedges can work now to help us out of this quagmire of indecision. Their approach has come to be called wedge analysis, or breaking down a large problem into smaller bite-sized pieces. By calculating the contribution of each wedge, we can add them up, see the magnitude of their collective effect, and decide that it's worth trying to move forward. The graph on the next slide is one that I think about often as I ponder this issue for myself and for my classes. As you can see from this graph, various solutions that are practical now basically provide a small slice. But if you add those slices together, you change the trajectory from the current path, which is to more increased emissions, to a path towards zero emissions. We could stabilize or even reduce carbon emissions now if we focus on multiple modest strategies. Doesn't this seem more doable to you? Okay, let's take a look at weather and climate. There's a difference between these two. Weather is a description of the physical conditions of the atmosphere in terms of moisture, temperature, pressure, and wind. Climate is a description of long-term patterns of weather. The atmosphere is a dynamic place. It retains solar heat and protects us from deadly radiation in space, and distributes the water that makes up most of our bodies. The atmosphere consists of gas molecules held near the Earth's surface by gravity and extends upward to about 500 kilometers. All of the weather we see is just in the lowest 10 to 12 kilometers, in a constantly circulating and swirling layer known as the troposphere. This troposphere is highly dynamic. The solar input comes in, gets distributed and changed. Some of it's reflected back, some of it goes into the atmosphere, all the way down to the troposphere. It gets absorbed and reflected inside that body of air. Water evaporates into the atmosphere, creating moisture in clouds. Those clouds rise, they condense, they form precipitation events. The world turns and distributes both these precipitation events, moves the atmosphere around, and also moves the currents of the oceans and circulates warm and cold water. So it creates a very dynamic set of processes that control our weather. So weather is the term for the short-lived and local patterns of temperature and moisture that result from all of this dynamic activity. In contrast, climate is the long-term patterns of temperature and precipitation. These will vary based on some other more long-term changes, such as oscillations that occur because of large movements of currents and temperature, but also slight changes in the Earth's rotation and the angle at which the Earth tilts and other things. Understanding the difference between short-term variations and long-term patterns is important in understanding our climate. As you learned in Chapter 14, and I hope you took a look at some of the YouTube videos that I posted there, our atmosphere is quite different now than earlier in Earth's history. The Earth's earliest atmosphere probably consisted mainly of lightweight hydrogen and helium. Over billions of years, most of that hydrogen and helium diffused into space. Volcanic emissions added carbon, nitrogen, oxygen, sulfur, and other elements to the atmosphere. Virtually all of the molecular oxygen that we breathe was probably produced by photosynthesis in blue-green bacteria, algae, and green plants. Clean, dry air is mostly nitrogen and oxygen, as you can see on this table. Water vapor concentrations vary from near 0 to 4%, depending on air temperature and available moisture. Minute particles and liquid droplets, collectively called aerosols, also are suspended in the air. Atmospheric aerosols are important in capturing, distributing, or reflecting energy. Particulates also have something to do with how much precipitation occurs by providing sort of collection particles around which water can condense. Also, our atmosphere is incredibly oxygen-rich, making large multicellular organisms like us possible. So this table, table 15.1, summarizes what I just outlined to you, the composition of the Earth's lower atmosphere, and this is our present composition. So our atmosphere is incredibly complex, with many levels, temperatures, and circulation patterns. This is a list of some of the topics that are discussed in this chapter, and it provides a good overview. So I'm going to just review some of these concepts. The sun supplies the Earth with an enormous amount of energy, but that energy is not evenly distributed over the globe. Incoming solar radiation, or what we call insolation, is much stronger near the equator than at high latitudes. Of the solar energy that reaches the outer atmosphere, only about 1/4 is reflected by clouds and atmospheric gases, and another 1/4 is absorbed by carbon dioxide, water vapor, ozone, methane, and a few other gases. This energy absorption is actually critical. Our world would be much colder without it. It warms the atmosphere. About half of the incoming energy reaches the Earth's surface. Some of this energy is reflected by bright surfaces such as snow and ice. These dynamics create an uneven pattern of heating on the Earth's surface. Warm air rises and it cools in the process, which causes water to condense and produce precipitation. Then the rotation of the Earth, in effect, sort of picks up these air masses and moves them around, creating the precipitation or storm events that we experience in different ways and at different times in our region, but also around the world. The Coriolis effect is the curving pattern that results from the fact that the Earth rotates in an eastward direction as the winds move around the surface. On a global scale, this effect produces predictable wind patterns and currents. On a regional scale, the Coriolis effect produces cyclonic winds, or wind movements controlled by the Earth's spin. Cyclonic winds spiral clockwise out of an area of high pressure in the northern hemisphere and counterclockwise into a low-pressure zone. If you look at the weather map, in the newspaper, you can probably find this spiral pattern. As a Californian, you probably remember El Nino and La Nina years. On another time scale, there are decades-long oscillations in the oceans and atmosphere. Both the ocean and the atmosphere have regular patterns of flow, or currents, but these shift from time to time. As the ocean currents shift, like water swirling in a bathtub, areas of warm water slosh back and forth. Sloshing in the ocean influences low-pressure areas in the atmosphere, and winds and rain change as a consequence. One important example is known as the El Nino Southern Oscillation, or ENSO. Significantly wetter winters are present in northwest Mexico and the southwest United States, including central and southern California. For the contiguous United States, potential impacts include above-average precipitation in the northern Rockies, northern California, and the southern and eastern regions of the Pacific Northwest as well. Below-average precipitation is expected across the southern tier, particularly in the southwestern and southeastern United States. This particular year, 2013, is shaping up to be an El Nino neutral year. You can monitor El Nino and La Nina by looking at the NOAA site, the National Oceanic and Atmospheric Administration site, that is updated and provided for you to monitor what kind of year we're having. There's also a Pacific Decadal Oscillation, or PDO. It involves a vast pool of warm water that moves back and forth across the North Pacific every 30 years or so. So this is a more longer-term oscillation. From about 1977 to 1997, surface water temperatures in the middle and western parts of the North Pacific Ocean were cooler than average, while waters off the western United States were warmer. During this time, salmon runs in Alaska were bountiful, while those in Washington and Oregon were greatly diminished. In 1997, however, ocean surface temperatures along the coast of western North America turned significantly cooler. perhaps making a return to the conditions that prevailed between 1947 and 1977. So some of our concerns about fisheries that we've talked about before are affected by these different oscillation phenomena. Convection cells occur because of uneven heating with warm air close to the equator and colder or colder air at high latitudes. This also produces pressure differences that cause wind, rain, and storms, and everything else we know as weather. As noted earlier, air circulation occurs as the sun warms the Earth's surface and air nearest the surface warms and expands, becoming less dense than the air above it. This rising warm air produces vertical convection currents. These convection currents can be small and as localized as a narrow column of hot air rising over a sun-heated rock, for example, or they can cover huge regions of the Earth, circulating air from warm latitudes to cool latitudes and back around again. So understand that these are actually currents, and you'll see from the maps in your book and future slides. These are sort of vertical, circular patterns that go up from the surface of the Earth. At the largest scale, the convection cells are described by a simplified model known as Hadley cells, which redistribute heat globally. Ferrel cells model the mid-latitude segment of the Earth's wind circulation. In the ferrel cell, air flows poleward and eastward near the surface, and equatorward and westward at higher altitudes. This movement is the reverse of airflow in the Hadley cell. Polar cells are part of a three-cell movement involving both the Hadley cells and the ferrel cells, which show atmospheric circulation and surface winds. These convection cells move around and change. At the top of the troposphere, our lower atmospheric layer, are jet streams. These are hurricane-force winds that circle the Earth. These powerful winds follow an undulating path approximately where the vertical convection currents as we described as the Hadley and ferrel cells meet. The Earth's rotation and winds also affect ocean circulation patterns. Warm and cold ocean currents strongly influence climate conditions on land. Surface ocean currents result from wind pushing on the ocean surface as well as from the Coriolis effect. As the surface water moves, deep water wells up to replace it, creating deeper ocean currents. Differences in water density, depending on the temperature and saltiness of water, also drive ocean circulation. Huge cycling currents called gyres carry water north and south, redistributing heat along with that from low latitudes to high latitudes. The Alaska current flowing from Alaska southward to California keeps San Francisco cool and foggy during the summer. The Atlantic currents actually make North America, the east coast of North America, and actually parts of the United Kingdom warmer than they ordinarily would have been. The Earth's tilt also changes or oscillates over very long periods of time. Climatologists have studied many data series like these and observed simultaneous repeating patterns of warming and cooling. The longest period cycles are called Milankovitch cycles, after the Serbian scientist who first described them. These cycles are periodic shifts in the Earth's orbit and tilt. The Earth's elliptical orbit stretches and shortens in a 100,000-year cycle, while the axis of the rotation changes its angle of tilt in a 40,000-year cycle. So you can see with all of these dynamics that our weather is very complex, and it will vary year to year, season to season, multiple years, and long term. So it's quite dynamic. So you can kind of understand without a background in weather and climate how maybe the public might get confused about the climate change issue. So this is a chart in your book that shows the layers of the atmosphere and how they vary in temperature and composition. So I think this is a very interesting graph, particularly as the temperatures increase and decrease as you go into these different upper layers. And as we've said in earlier slides, and the book illustrates that most of the weather occurs in the troposphere. This slide shows figure 15.5 in your book, and basically gives you a breakdown of the balance of insolation, that is the incoming solar energy starting at 100%, and how it's changed and reflected back and reabsorbed on the Earth's surface. Energy balance between the incoming and outgoing radiation is illustrated here. The atmosphere absorbs and reflects about half of the solar energy reaching the Earth. Most of the energy re-emitted from the Earth's surface is long wave or infrared energy. So the wavelengths actually change from this absorption and reflection. Most of this infrared energy is absorbed by aerosols and gases in the atmosphere and is re-radiated back towards the planet, keeping the surface much warmer than it otherwise would be. So this is how the greenhouse effect works. So some of this, these aerosols and gases are actually beneficial. Our planet would be much colder without it. So the question becomes, as we increase these, how dangerous does this greenhouse effect get to our biosphere, and particularly our human civilizations? So one of the things that is a little hard to explain, but also is something that is compounding our problem, is that there's a positive feedback loop for warming going on. This is not good for us. The Arctic Ocean is covered with ice and acts like a giant mirror, reflecting solar radiation back into space and keeping the planet cooler. That's obviously melting sea ice is going to reduce this effect. Surfaces that reflect energy have high albedo, or reflectivity. Most of these surfaces appear bright to us because they reflect light as well as other forms of radiative energy. Surfaces that absorb energy have low albedo and generally appear dark. Black soil, pavement, and open water, for example, have low albedos. So the overall temperature of the biosphere is sort of balanced by this high albedo, low albedo surfaces on our planet. So as we reduce the Arctic ice, we're compounding the problem because the reflectivity of our ice sheets go down. Now, if you were to increase those ice sheets, it would lower the temperature of the Earth's surface. Water is extremely efficient at absorbing and storing energy. This is why increasing open water at the poles worries climatologists. For hundreds of thousands of years, the Arctic has been mostly white, reflecting most energy that reached the icy surface. Now open water increasingly captures and stores that energy, further accelerating ice melting and atmospheric warming. This is why we have a positive feedback loop, which means that melting leads to further melting. So that's why one of the wild ideas about space-based or other technical solutions is to use different kinds of reflectors to increase albedo and combat climate change, as we mentioned when we opened this chapter. So this is a table that shows the reflectivity or albedo of surfaces. So as you can see, black soil, pavement, and open water, for example, have low albedos. This is a map of the convection cells that I mentioned in the previous couple of slides. Convection cells circulate air, moisture, and heat around the globe. Jet streams develop where the cells meet, and surface winds result from convection. So convection cells expand and shift seasonally. So you can kind of interpret how we get some of the weather patterns that we do here with looking at the directions, the basic directions of wind patterns and the circular position of these cells, and then you can see how the polar jet streams, these high-powered winds, sort of propel storms around. And all of this is shifting, of course. So winds and weather redistribute heat. Evaporating water consumes about 580 calories of heat per gram. So enormous amounts of heat are transferred to the atmosphere over the tropics, because the tropics get the most intense insolation from the sun. Winds from the Earth's rotation transport this humid air north towards the cooler regions, where heat and moisture are delivered to continents in rain or snow. Without this circulation, these areas would be much colder and the Earth would experience much greater temperature extremes. So this process is a little bit more fundamental to life on Earth, and some of the moderation in weather that we currently enjoy where we live. So this diagram kind of shows how this process works. Convection currents distribute heat that's in evaporated water around the globe. When it's hot, moist air rises. It creates low pressure at the surface. So as this hot, moist air rises, it expands and cools, then moves towards higher pressure. So as the pressure goes up, it sinks, warms, and evaporates moisture. So high pressure at the surface moves to low pressure at the surface, creating this sort of circular vertical convection current that I talked about. This is a typical pattern of a jet stream. This is the Arctic circumpolar vortex. This large circulating mass of cold air sends fingers or lobes across North America and Eurasia, spreading storms in their path. If the vortex becomes stalled, weather patterns stabilize, causing droughts in some areas and excess rain elsewhere. This is a current jet stream forecast for the United States, including California, that I downloaded for Monday, March 15th. So very often on the weather reports you see them reporting that the jet stream is moving around and it steers storms in our direction or away from our direction. Our actual weather events that we experience are created by frontal systems. So frontal systems create local weather. The boundary between two air masses of different temperature and density is called a front. When cooler air pushes away warmer air, we call the moving boundary a cold front. Cold, dense air of a cold front tends to hug the ground and push under the lighter, warmer air as it advances. As the warm air is forced upward, it cools, and its cargo of water vapor condenses to water droplets or ice crystals. Air masses near the ground move more slowly because of friction and turbulence near the ground surface. So upper layers of moving air mass often move ahead of lower layers. In a warm front, the advancing air mass is warmer than the surrounding air. Because warm air is less dense than cool air, an advancing warm front will slide up over cooler air masses, creating a long wedge-shaped profile with a broad band of clouds and precipitation. In California, of course, we have a rainy winter and a dry summer. In the winter, we get cold fronts that pass over our state from roughly October 1st to July 1st. In the summer, there's the convection currents and the weather circulation causes the northward migration of a semi-permanent Pacific high that sets up in the summer that diverts more storm tracks to the north. So we rarely get rain in the summer because of that. Even though we talk about the potential dramatic effects of the current climate change issue, climates have changed dramatically throughout history. I don't think this is a reason to be complacent or deny climate change, however. We know this because every time it snows, small amounts of air are trapped in snow layers. In Greenland, Antarctica, and other places where cold is persistent, yearly snows slowly accumulate over centuries. New layers compress lower layers into ice, but still tiny bubbles remain, even thousands of meters deep into glacial ice. Each bubble is a tiny sample of the atmosphere at the time that snow fell. Climatologists have discovered that by drilling deep into an ice sheet, they can extract ice cores from which they can collect air bubble samples. Ice cores are an important source of climate history and one of the key sources of evidence to understand climate change. Ice core data also show that the climate is warmer now than it has been since the development of civilization, agriculture, and urbanization as we know them. We know from historical accounts that slight climate shifts We know from historical accounts that slight change in climate shifts can be destabilizing for human communities. During the Little Ice Age, which began in the 1400s and ended at about 1815 or so, was a cooling trend that caused crops to fail repeatedly in agricultural regions of northern Europe. There's a really interesting documentary that you can get from the History Channel called The Mini Ice Age. I suggest you watch it. Scandinavian settlements during this time in Greenland, founded during the warmer period around AD 1000, lost contact with Iceland and Europe as ice blocked shipping lanes. The cycles defined earlier complicate the story. Even with climate change, at some point another ice age will occur. Ice ages occur when these oscillations are aligned in such a way as to cause ice to build up, increasing albedo, as we've discussed, and then tipping the Earth into an ice age. That's why I think some of these wild ideas about creating reflection devices might cause more problems for us. You know, we want to manage climate change, but we don't want to tip ourselves into an ice age. The predictions about the next upcoming ice age vary, but another ice age should start about 10,000 years from now, based on this alignment of these different oscillations that we have been discussing. So this graph, figure 15.4 in your book, shows our best data about carbon dioxide and temperatures from some of this long-term data that we've been discussing. And at this point, many scientists regard human-caused or anthropogenic climate change to be the most important environmental issue of our times. Measurements of atmospheric carbon dioxide taken at the top of Mauna Loa, Hawaii, show an increase of 1.5 to 2.5% each year in recent years. For carbon dioxide, monthly mean, which is in the red, and annual mean, so I need to correct this for a minute. I said Mauna Loa, I meant Bostock. These long-term ice core information, the data shown in red is the carbon dioxide levels recorded in the atmosphere, and the blue are the temperature recordings. And you can see that although it oscillates, the carbon dioxide levels are just showing an accelerating and rapid change, and the temperatures are reflecting that. Now the big question is, what's going to happen to temperatures when they catch up to this peak shown in the red? So the recent climate changes are unusually rapid, and that's what is of concern to climate scientists. So the main body that, and I think we've mentioned it before, but the main body that looks at these things is called the IPCC. This is the Intergovernmental Panel on Climate Change. They have a really good website. I got it up on my website for the course. And it's tried to put together this body of information that we have and assess data on climate change and provide information for policymakers. It uses the best expertise that we have available from over 2,500 scientists. Their annual report 4, it's not an annual report, or assessment report 4, that's what it's called, predicted that there would be a 2 to 4 degrees centigrade rise. That translates to 3.8 degrees Fahrenheit by 2100. That was a report that was produced in 2007. Along with this, they predicted a possibility of 1 meter or 3 foot, with a possibility of 2 meters or 6.5 foot sea level rise by 2100. This has been revised in 2009. The 5th assessment report will be finalized in 2014. On the web, there is a content discussion of that 5th report available on the IPCC site, and I also put that link on my website. So these are the measurements of atmospheric carbon dioxide that's been taken at the top of Mauna Loa, Hawaii. And you can see the curve that is shown here. It's an increase of 1.5 to 2.5% each year in recent years. And for carbon dioxide, the monthly mean is shown, so you can see how it fluctuates up and down, and carbon dioxide does do that, and the annual mean in black is shown. But you can see the overall trend is up. Temperature represents a 5-year mean variation from 1950 to 1980, and you can see temperatures are rising as well. So this is figure 1518 in your book, and shows an approximate change in land surface with the 1 meter, that is the 3-foot sea level rise, that the IPCC says is possible by the year 2100. So one of the current aspects of debate, and many are anxiously awaiting the assessment report number 5, because there's been a lot of discussion about the sea rise issue accelerating and trending towards the maximum sea level rise rather than a median or minimum sea level rise. So that's being discussed in the literature. But you can see the impact on our coastal low-lying regions with this map. And I'll reproduce the projected sea level rise in our own county, in San Mateo, from the Bay Area Conservation and Development Commission's climate change site. So you can see how the sea level rise will impact our own area. Now the light blue here is based on a 16-inch rise, and the blue additions, the dark blue additions that you see, are based on a 55-inch sea level rise. So I think this chart illustrates that climate change is not a faraway issue, primarily affecting the East Coast and affecting low-lying Pacific Islands and other places far away. This is also a surface temperature projection from the IPCC scenario B1. That's the actual number. If you look at their detailed analysis, they take different scenarios or different possible outcomes and they analyze them. This scenario assumes that global population peaks in the mid-century and declines thereafter. So it infers some rapid introduction of newer, cleaner, and more efficient technologies that help the climate change issue, but without additional climate initiatives. So let's look at the climate change in a little bit more detail. Carbon dioxide is the most important greenhouse gas. Emissions have doubled from 1970 to 2010. Fossil fuel burning is the major human-caused source of carbon dioxide. But carbon dioxide is not the only greenhouse gas. Methane is a more potent greenhouse gas, and ruminants, that is cattle raising and cattle feedlots and dairy farms, and rice paddies are the sources of methane. Methane is more potent than CO2, but it's not as abundant in the atmosphere as CO2 is. Nitrous oxide comes from vehicle engines and agricultural processes. And it is even more potent, but again, not as abundant in the atmosphere. But we have to actually look at all of these three. You can actually compare these two by using converting them to CO2 equivalents. So your book gives a more extensive discussion of these three greenhouse gases, and I suggest you look at that. One way to compare the importance of the different kinds of greenhouse gases is to convert them all to equivalents of our most important greenhouse gas, which is carbon dioxide. The units used on the y-axis in this figure, figure 19, let us compare the effects of these different sources. So all four sources looked at here, CO2 is divided between fossil fuel use and deforestation and decay, have risen between 1970 and 2010. This is the reason why transportation and coal-burning power plants are two of the key sectors that need to be addressed in order to slow climate change. A big part of the IPCC work is modeling with the best available methods, and so they've actually, much of their information is based on computer models. And these models look at a lot of data. They work with a lot of consensus among scientists, and they run to give us some ideas of how we can predict changes in climate and then develop policies off of that. So when you add up all of this evidence, the idea that climate change is occurring and can affect human civilization is overwhelming. As best as can be determined, I'm going to read this, quote this, "The world is now warmer than it has been at any point in the last 2 millennia. And if current trends continue, by the end of the century, it will likely be hotter than any point in the last 2 million years." And that's the concern that is a little bit difficult to get a grasp around. The end of the millennia means that many of us will be long gone, and more of us, the younger of us, will be quite aged by then. So it's hard to think about, these events looking at the end of the century. But most of us have children or will have children and grandchildren, so I would think about it in that perspective. So these are the observations of climate change, so I'm going to go through them. The average global temperature has climbed 1 degree Fahrenheit in the last century. 19 of the 20 warmest years in the past 150 years have occurred since 1980. The poles, that is the North Pole and the South Pole area, the Arctic and Antarctic, are warming the fastest. Now that's where our ice is, right? That affects albedo. Permafrost is melting in Alaska and Canada, and houses, pipelines are being damaged, and trees are being toppled. Now, permafrost is permanently frozen subsoil, which we talked about in one of our farming chapters, and also we talked about it in the biological chapters. Melting permafrost means decomposition occurs, and when decomposition occurs in conditions of lack of oxygen, that is down in the soil, you release more methane. So there's a concern that the methane releases will be increased by a warming planet. So that's kind of another compounding factor that we need to think about. Arctic sea ice is half as thick as it was 30 years ago, and the ocean area covered by ice has decreased by 1 million square kilometers in 30 years. More open ocean, less albedo, the planet warms. Polar bears are dying as they attempt to find pack ice, which is declining on which to hunt. Polar bears, kind of do the opposite of your typical brown bear. Their sort of feeding season is in the winter when the pack ice is present, and their sort of hibernation season, although they don't hibernate, is the summer when they don't have access to hunting on pack ice. So the less ice, the less polar bears. Antarctic ice shelves are disappearing. Penguins declined 50% in the last 50 years. Many of you probably enjoyed and watched the March of the Penguin film that was such a great documentary about penguins, the emperor penguins in particular. That specific population that was featured in that film has also declined by 50% since that film was made. The oceans are absorbing and storing more heat. Sea level has risen 15 to 20 centimeters in the last century. A lot of the damage that was done by Hurricane Sandy was in part because of rising sea levels. Oceans are absorbing some of the extra carbon dioxide, but that is acidifying the ocean and damaging the corals. And one of the things that we've mentioned is that coral reefs are one of the more productive ecosystems out there, and they sequester some greater amounts of carbon, which removes carbon dioxide from the atmosphere. This is a slide looking at Grinnell Glacier from 1922 to 2008. And you can see Grinnell Glacier is actually found in our own Glacier National Park. And you can see the change or the melt that's going on with this glacier in our own country. This is being observed around the world. Growing seasons are lengthening in the northern hemisphere. Some animals are breeding earlier or extending their range, and that, of course, means others are disappearing. Droughts are more frequent and widespread, and storms are more severe. The predictions for climate change in our own state, California, sort of centers around this point. The predictions are that we will have more severe droughts, and we'll have some more severe storms when we do get our wet years. So in some sense, our state is somewhat unprepared for very severe storms and also extremely severe and long droughts. Animal breeding and migratory schedules are changing. Some of these may hurt these species. Some species are declining or going extinct during warming temperatures and loss of habitat. The polar bear and the penguins are a specific example. Global warming will be expensive. At present, reducing greenhouse gas emissions could cost 0.5% of the world GDP, according to one report. The IPCC report states a figure a little bit less than that. But in a time where we're struggling with our economy, this is probably an expense we don't need. If we delay, it could cost as much as 20% of world GDP. Any energy production will need to be 80% decarbonized by 2050 to stabilize the climate. That's not too far away. Those in richer countries will be able to blunt the effects of climate change, but the poorer countries will suffer the most. And again, that is a little bit of an environmental justice issue. So your book talks about 4 steps for combating climate change. Implement emissions trading, technology sharing with less developed countries, reducing deforestation, and helping poorer countries respond to climate change. I think the most significant effect we need to worry about is the rise in sea levels, which has the potential to disrupt many communities. Although I have, scientific and sort of personal and ethical concerns about impacts on biodiversity and species and these other effects, the sea level rise should give even the most skeptical and critical of us pause. I've showed you the map of San Mateo County, and you heard about the recent hurricane devastation on the East Coast. So, these things can impact and hurt many people. Okay, so we talked about this sort of doom and gloom scenario about climate change. Let's look at how we envision solutions. In 1997, a meeting in Kyoto, Japan, called together climate scientists and government representatives from around the globe. This meeting was a follow-up to the 1992 Earth Summit in Rio de Janeiro in Brazil, at which most nations had agreed in principle that sustainable development, equitable growth that doesn't destroy opportunities for future generations was a good idea. The Kyoto Protocol followed this general principle and called on nations to roll back emissions of carbon dioxide, methane, and nitrogen dioxide. The goal was to reach 5% below 1990 levels by 2012. Poorer nations then, such as India and China, were exempt, allowing them to expand their economies and improve their standards of living. The Kyoto Protocol went into effect in 2005. Each country signing the agreement is now responsible for following through and reducing emissions. Considerable progress has occurred, especially in Western Europe, but most countries are behind their Kyoto targets. Among the developed nations, only the United States and Australia still declined to sign the protocol. The United States has persistently claimed that reducing carbon emissions would be too costly, and we must put the interests of our own country first and foremost. Many other smaller agreements have followed Kyoto. So although not all countries have really bought into this, it still is perhaps a goal and a guideline that we can work towards. An option for controlling emissions is carbon trading. Carbon trading has been implemented in some markets around the world, and it does operate in North America to some extent. It's not formally used or established in the United States, however, although it's been debated in Congress. In carbon trading, and the other term for it is cap and trade systems, legal limits are set on emissions. In countries with lower emissions, or utilities or companies can sell their emissions credits to others, or their right to pollute to someone else. The Kyoto Protocol promoted this approach. The global market for trading carbon emission credits has grown rapidly. In 2006, about 70 million tons of carbon equivalent credits were exchanged, with a value of some 3.5 billion. The idea is that companies that have carbon credits can sell that to another company that needs them. So that provides a source of monies that can be used to reduce carbon emissions. In order to avoid having to purchase credits, some companies may choose to lower carbon options on their own. Now we can get back to the stabilization wedges concept that we introduced earlier. By utilizing wedge analysis, the problem of climate stabilization can be broken down into smaller bite-sized pieces. To stabilize carbon emissions, we need to cut 7 gigatons over the next 50 years. Doubling vehicle efficiency and halving the miles we drive would save up to 1.5 gigatons. Installing energy-efficient appliances, lighting, and insulating buildings could save another 2 gigatons. Capturing and storing carbon emissions from power plants and gas wells could save another gigaton. So you kind of add that up, and what do you get? 2, 3.5, 4. That gets us a little over halfway there. This table gives a guideline and some specifics about stabilization wedges that we could use. As discussed in the opening case study, the idea of stabilization wedges is that they can work just by expanding currently available technologies and practical solutions that we have. To stabilize carbon emissions, we would need to cut about 7 gigatons in 50 years, as we stated in the previous slide. Because most of our CO2 emissions come from fossil fuel combustion, energy conservation and a switch to renewable fuels are important. We're going to get to looking at energy pretty soon, and we'll take another look at renewables when we get there. Doubling vehicle efficiency and halving the miles we drive would add up to 1.5 of the gigatons that we need. Installing efficient lighting and appliances and insulating buildings could add up to another 2. And capturing and storing carbon released by power plants, gas wells, and other sources could save another gigaton. So all of these are possible. Your book states that carbon and capture and storage is beginning to be practiced. Some companies like Norway are pumping carbon dioxide into an aquifer beneath the seafloor to store carbon. If carbon is sequestered, the company avoids carbon taxes on emissions and increased pressure on oil reserves enhances oil recovery. So carbon capture and storage is brought up as one of the important stabilization wedges. And this is actually being looked at around the world, but it has not really caught on in the United States yet. This diagram shows how it might work, and you can take a look at that. You can pump it into deep aquifers. One of the other methods that I've seen used, and there's a series of films, if you can get access to the History Channel. I know they're not on Netflix yet, but called Environmental Tech, that also illustrates some of this. But one of the other ways I've seen it done is you use carbon dioxide in a bioreactor, and you basically grow algae, and then you use the algae for other products such as fertilizer. So that's another way that it can be done. And the other question is, should we focus on methane? Methane is a more powerful greenhouse gas. Methane from landfills, oil wells, and coal mines is now being collected in some places for fuel. Rice paddies are another major methane source. Reducing gas pipeline leaks would conserve the resource as well. Ruminant animals could be reduced, and modifying human diets would also help to reduce methane significantly. Our own county landfill, which is at Ox Mountain, which is on the way to Half Moon Bay off of 92, actually has a power plant that captures methane from the landfill and uses it to generate a modest amount of power. Regions are actually taking on this this issue. And I sometimes think that with failure of some of the nations to act, the regions are may be more effective at solving climate change. California has a state climate change portal, and a number of federal agencies have climate change websites. But California is working a little harder than this than the rest of the nation. So conservation and renewable energy offer our best solutions to this problem. And your book gives a pretty good overview of what some other countries are doing. So the question is, what can you do? So this is a diagram in your book that kind of shows potential emissions reductions of these different techniques. So I would take a look at some of these and see if there's things that you think that you can do as an individual to help solve our climate change problem. So this is the end of a long chapter. Climate change may be the most far-reaching issue in environmental science today. Although the challenge is almost inconceivably large, as we have pointed out, solutions are possible if we choose to act as individuals and as a society. Understanding the climate system is essential to understanding the ways in which we can solve the climate change problem. And despite the importance of natural climate variation, observed trends in temperature and sea level are more rapid and extreme than other changes in the climate record. And as I pointed out, the sea level change is probably one of the more disruptive issues that we have to deal with that could take place in decades, independent of long climate change events. The main issues that we have to think about are increasing use of fossil fuels and forest clearing and decomposition of agricultural soils and increased methane production. International organizations, national governments, and local communities have all begun trying to reverse these changes. Individual actions and commitment are also essential if we are to avoid dramatic and costly changes in our own lifetimes.